Welcome back. In the last lecture, we finally succeeded in proving that the Heisenberg group, equipped with the Carnoy-Carathédry distance, is indeed a metric space. This distance, its definition, comes from what we called horizontal curves and their length. We also succeeded in showing some estimate for the distance to the origin. Now, when you are in a metric space, no matter where the distance comes from, there is this intrinsic notion of length through partitions of the curve. So you have your distance in the metric space, you have a curve, you partition it into finite many pieces, and you look at the supremum. If this supremum is finite over all partitions, then you call the curve rectifiable. And you call that value of supremum the length of gamma. Now, because in the Heisenberg group we also started with this notion of horizontal curves, we wonder what is the connection between the two. Are horizontal curves rectifiable? What other curves could be rectifiable? And whether the space is geodesic, meaning that given any 2 points P and Q, there is a curve so that the distance of PQ is exactly the length of P. There exists a curve whose length is equal to that distance. And this length is now the intrinsic distance defined up here through supremums. And the answer to these questions are very well written in a paper that I will mention in a second. But let's prove one direction of the first claim, that horizontal curves are rectifiable. So if gamma from AB into H1, say, is horizontal, then it is rectifiable. And the length of gamma, in the sense of rectifiability, is no more than the length of gamma with respect to the sub-Riemannian metric. Okay, proof. You take your gamma, of course this is a simplistic picture, and then you take a partition. You have to prove the bound for every partition. Okay, so suppose this is gamma ti, this is gamma ti plus 1. Now we have some estimate on distance of gamma ti from gamma ti plus 1. So this is equal to infimum of the length of all gamma tilde g, where gamma tilde is horizontal and joins gamma ti to gamma ti plus 1. This is definition of Carnoy-Carathédry distance. Because this is an infimum and gamma restricted to interval ti plus 1 is one example of a horizontal curve between the ends that we want, length g of that portion of gamma is an upper bound. So this is true for every I in my partition. Now if you add these up, gamma ti and gamma ti plus 1 over I, then this becomes less than summation of length of subcurves, but these are separate intervals, there's no overlap, so this becomes in total it becomes length of gamma. And now we see that this was independent, the left hand side is independent of the partition or choice of ti, So even if you take supremum, that becomes still less than. So gamma ti plus 1, and over any partition is less than Lg of gamma. And that by definition, this means gamma is rectifiable. And length of gamma, which is by definition equal to that supremum, is less than length horizontal sense of gamma. This is a very well-written paper by Piotr Hajwasz and Scott Zimmerman. The title is Geodesics in the Heisenberg group. The statement that we just proved is contained in part 1 of proposition 1.1. If you have any horizontal curve, then it is rectifiable, and its length in the sense of rectifiability, which is written here as LCC, is equal to the length of the horizontal curve with that metric that we equip R3 with. Part 2 says that if you have a Lipschitz curve, and Lipschitz here uses the distance Carnot-Karre theory. If you have a Lipschitz curve, then it is horizontal. Because Lipschitz curves are absolutely continuous, that checks the first criteria of horizontality. The second bit is that the derivative, the velocity, lies in the horizontal subspace almost everywhere. Third, if you start with a rectifiable curve, it is true fact in any metric space that you can reparameterize it to become one Lipschitz. So in particular in Heisenberg group, if you start with the rectifiable curve, you can reparameterize it to be one Lipschitz. Now this together with part 2 says it then coincides with a horizontal curve. If you ignore the reparameterization story here, and if you look at basically the trace of the curves, it shows that rectifiable curves follow exactly the path that the horizontal curves travel. For example, going along the t-axis will not give you a rectifiable curve because it's not horizontal. The proof of this proposition is completely written out in this paper with all the details, as are the proofs of the structure of geodesics. So in this paper, using some Fourier analysis technique, there has been explicit calculations of what the geodesics are, not in H1 but also in Hn. So Heisenberg group with the Carnot-Karre theory distance is geodesic. Given any 2 points, there does exist some curve between them that is rectifiable, and its length is equal to the distance of the endpoints. It is in general true that you cannot find any shorter curve. This strict inequality can never happen. So this is as fast as you can afford to get from P to Q. Being geodesic is a pleasant, important property in a metric space, and Heisenberg group checks that one.